Hey there, 10th graders. Welcome to today's Explainer. I am so excited to be your guide as we dive into one of the most fascinating topics in your science syllabus, ordinary chemical reactions. Now, I know chemistry can sometimes feel like this giant, abstract alphabet soup of letters and numbers, but today, we're going to completely ground it in reality. We're breaking these concepts down step by step on our glowing blackboard, making sure you walk away totally confident and ready to ace those exams. Let's get right into it. So here is our game plan for today. First, we'll look at everyday chemistry in action. Second, we'll map out the core concepts and dependencies. Third, we'll dive into some real-life chemical reactions, followed by how to actually identify them. Then, we'll cover the essential chemical formulas you need to know. And finally, we'll squash some common misconceptions and share a handy memory trick.
All right, Section 1, Everyday Chemistry in Action.
You know, it's really easy to think of chemical reactions as these abstract ideas confined to highly controlled labs with people wearing safety goggles. But the truth? They are happening all around us, literally every single second. From the food sizzling on your stove to the complex cellular processes keeping you alive right this very moment. Chemistry is this vibrant, continuous phenomenon. It's basically the invisible engine driving the entire world we interact with.
Moving on to Section 2, Core Concepts and Dependencies. Okay, so the absolutely crucial thing to grasp here is how these concepts depend on each other. Any big, physical, macroscopic change you observe with your own eyes, that actually relies on unseen, microscopic shifts down at the atomic level. Chemistry is fundamentally a story of transformation. The stuff you start with, we call those reactants, literally break their bonds and rearrange themselves. Through this incredible process, entirely new substances, called products, are formed. And almost always, during this grand atomic reshuffle, energy is exchanged. It's either absorbed from the environment or released out into it. You simply cannot get that visible change without the invisible atomic shift happening first.
Let's jump into Section 3, Real-Life Chemical Reactions.
Let's look at two super common examples. First, think about milk spoiling. When you leave milk out at room temperature, it's not just getting warm. There are bacteria in there actively feasting on the lactose sugar, breaking it down into lactic acid. This causes a huge drop in pH, making the proteins clump together into curds and creating those incredibly sour compounds. That is a full-blown chemical reaction. Now compare that with iron rusting. When a fresh piece of iron is exposed to the oxygen and moisture in the air, a reaction kicks off. The iron physically transforms into a reddish-brown flaky material, iron oxide. These are two totally different everyday events, but they are both driven by the exact same principle: reactants transforming into entirely new products. And we can see this brilliantly with even more delicious everyday chemistry. Think about the magic of fermentation. Yeast actively breaks down natural grape sugars, and the newly formed products are alcohol, carbon dioxide, and energy. Or what about basic food chemistry, like frying an egg or baking bread? The heat denatures the proteins, breaking them down into simpler molecules. There's also the Maillard reaction, where amino acids and sugars combine under high heat to create browning and those amazing savory flavors we all love. It is literally delicious chemistry. But honestly, the most vital chemistry of all is happening inside you. Think about digestion. Your body uses enzymes as catalysts, and they act like tiny molecular scissors. They chop up complex proteins into amino acids, carbs into simple sugars, and fats into fatty acids. Why? To fuel cellular respiration. Your cells take that simple sugar, glucose, combine it with the oxygen you breathe, and chemically react them to produce vital energy, plus carbon dioxide and water. That specific chemical reaction is what's keeping every single living cell in your body alive right now.
Section 4, Identifying Chemical Reactions.
Now, when you're sitting in your exam, you need to know the official scientific indicators that prove a reaction has actually taken place. I want you to memorize this foolproof acronym, GSTCP. That stands for gas evolution, state change, temperature change, color change, and precipitate formation. If you observe one or more of these signs, you can confidently say, yep, a chemical transformation just happened.
Let's map some real visual examples of the GSTCP acronym. For color change, imagine brilliant purple potassium permanganate turning totally colorless the second you add citric acid. Or for gas evolution, picture hydrogen gas bubbling up vigorously when zinc meets sulfuric acid. We see state changes when solid candle wax combusts into liquid and gas. And temperature change, that's perfectly demonstrated when quicklime reacts with water, releasing a massive amount of heat energy. These are your undeniable rock-solid clues.
Section 5, Essential Chemical Formulas.
Let's break down that zinc and sulfuric acid reaction we just talked about.
Our reactants are solid zinc, written as Zn, plus aqueous sulfuric acid, H2SO4. When they react, they form our products, aqueous zinc sulfate, ZnSO4, and hydrogen gas, H2. Now I want you to notice the upward arrow written right next to the H2. That is such a brilliant way to illustrate our GST-CP indicator for gas evolution. In chemistry shorthand, that upward arrow just means a gas is bubbling up and escaping into the air. Next up, let's walk through that stunning color change equation. We start with potassium permanganate and citric acid as our reactants. Now, the balanced equation shows them transforming into a whole new set of products, including 3-HMNO4 and a complex potassium citrate compound. Listen, you don't need to memorize every single atom of this giant organic equation right this second. The crucial takeaway here is the visual indicator. This specific chemical rearrangement takes a bright purple solution and turns it completely colorless. The actual molecular structure shifts, and because of that, the way it absorbs light changes completely.
Finally, let's look at a classic precipitation reaction. We start out with two totally clear watery solutions, barium chloride, BaCl2, and sulfuric acid, H2SO4. But when you mix them together, something incredible happens. They basically swap partners to form hydrochloric acid and barium sulfate, BaSO4. Now, because barium sulfate does not dissolve in water, it instantly crashes out of the solution as a white solid. That solid is what we call a precipitate. And just like we used an upward arrow for gas, you'll often see a downward arrow, or a little letter S for solid, to indicate that a precipitate just formed. All right, our final section, misconceptions and memory tricks.
There is a really common misconception I see all the time. A lot of students think rust is just dirt or grime that sort of gathers on the outside of old metal. But in scientific reality, rust is not an external coating at all. It is the actual metal transforming. The iron atoms literally bond with oxygen and moisture from the air to create a brand new chemical substance, iron oxide. The original iron is actually being consumed in the process.
Another huge pitfall is sour milk. It's so easy to just think, oh, it got warm, so it changed its physical state, kind of like ice melting into water. No way. The reality is there's a microscopic turf war happening in your glass. Bacteria are actively breaking down the lactose sugar into lactic acid. It's this newly formed acid that drops the pH and chemically forces those proteins to curdle. It's a one-way chemical street, not just a simple physical phase change.
So, how are you going to remember all of this when the pressure is on in the exam hall? Just lean on our trusty trick from earlier, GSTCP. Whenever a question asks you to provide evidence for a chemical reaction, just run through those 5 letters in your head. Is there gas evolution, a state change, a temperature change, a color change, or precipitate formation? If you can list those 5 indicators, you are absolutely going to nail those questions.
And that brings us to the end of our lesson on the glowing blackboard. But before you log off, I want to leave you with something to think about. What essential chemical reaction, the one that turns glucose and oxygen into energy, is keeping every living cell in your body functioning right this very second? That's right, it's cellular respiration. You are literally a walking, talking, thinking chemical reactor. Chemistry isn't just trapped in some textbook, it's happening inside you right now. Keep observing the world, keep asking those big questions, and I'll catch you in the next explainer.